So one thing that I've seen a lot of organic chemistry professors not do a great job of is teaching students how to clearly distinguish between whether or not a reaction will go SN1 or SN2. I think the reason that we professors shy away from doing this is because there are often tons and tons of exceptions. Nevertheless, I like to make things easy for my students, so I'm going to teach you some general rules that are right about 90% of the time. Now, I promise that as you apply these rules and think about why they actually are the way they are and what they actually mean, you'll gradually develop the fluency needed to be able to pick out the exceptions over time. So here's the way I teach my students to distinguish if a reaction is going to go SN1 or SN2. I just ask a series of questions. Question number 1 is this: is the carbon bonded to my leaving group primary, secondary, or tertiary? If it's a primary, then the reaction goes SN2. If it's tertiary, then the reaction is SN1. If it's secondary, or if it's a stabilized carbocation such as an allyl or a benzyl carbocation, then it could be either of the above. Now let's pause for a moment and see if we can actually figure out why this statement is the way it is. Keep in mind that in an SN1 reaction, the leaving group has to leave first and give me a carbocation. Is that ever going to happen on a primary carbon? The answer is no, because primary carbocations are so unstable. Instead, that will just sit around, the leaving group will never take off, and wait for my nucleophile to come in and kick it off and take its place, which is SN2. Now, by comparison, if I've got my leaving group stuck to a tertiary carbon, is that ever going to go SN2? The answer is no way, because a nucleophile in an SN2 has to be able to come into that carbon and displace the leaving group in a single step. It will not do that because a tertiary carbon is too hard to get into because it's got carbons all around it, which really get in the way, whereas a primary carbon has just hydrogens. Now, as I pointed out, if it's secondary or if it's a stabilized carbon, such as a benzyl or allyl carbon, then it could either be SN1 or SN2, depending on whether or not the reacting nucleophile is strong or weak, which I'll talk about momentarily. So these pictures kind of sum it all up. If I've got a leaving group stuck to primary carbon, it's going to be SN2 or E2. Now keep in mind, E2 is something we'll talk about in the next chapter, so at this point you don't have to freak out about it. If I've got a tertiary carbon, it's going to be SN1, E1, or E2. Please ignore the E1 or E2 at this juncture. And if it's any of these guys, then it could be any of the above. So that's our first question. Once again, we just ask ourselves, is the carbon stuck to my leaving group primary, secondary, or tertiary? If it's primary, it's going to go SN2. If it's tertiary, it's going to go SN1. If it's secondary, it could be either or. But which one will it be? The answer depends on my nucleophile or base. So this brings us to question number 2. Is my nucleophile strong or weak? Now you might be wondering, what in the world does that mean? Strong nucleophiles have negative charges. The exception are negative charges on halogens or negative charges that are resonance stabilized. Those negative charges are weak. If you have a nucleophile that's strong, then your reaction will be an SN2 reaction. If it's weak, then your reaction will be an SN1 reaction. So let me clarify that a little bit. Keeping in mind that in an SN2 reaction, what occurs is the nucleophile comes in and attacks a carbon and kicks off a leaving group. Wha-bam! The nucleophile that reacts has to be strong and powerful and potent to be able to do that. The nucleophiles that are strong and powerful and potent are guys who have localized negative charges. And they can't be negative charges on halogens or on molecules where the negative charge is smeared across a bunch of atoms. That is, a negative charge is resonance stabilized. Imagine I've got an iodide, an I-. Is that a supremely reactive nucleophile? If I've got an I- floating around, I'm going to be scared of it. Oh no, it's an I-. Ah! No, of course I'm not going to be, because an I- is weak. Iodides can handle a negative charge and not be reactive hardly at all. So they will be weak nucleophiles. Same thing with Br-, same thing with Cl-. Now what about an OH-? If I've got a minus charge on a hydroxide, is that a strong nucleophile? Well, let me ask you, would you want to bathe in sodium hydroxide? Yeah, probably not. Why? The reason because hydroxide is strong and reactive because there's a localized negative charge on that oxygen. Whereas if I've got a negative charge on a halogen, not going to be very strong. So here's a chart showing some examples of strong nucleophiles, which are once again going to be the guys who participate in SN2 reactions. If I've got M stuck to cyanide, M stuck to OR, OH, SR, NR2, or R. Or M is a metal, either lithium, sodium, or potassium, and R can be any alkyl chain. These are all extremely strong nucleophiles. I want to emphasize something here. If you see a lithium or a potassium or a sodium, because it's in group 1 of the periodic table, you know it's going to want to give up its electron to whatever atom it's bonded to so that it can become a cation and feel like a noble gas in column A to the periodic table. Thus, if I see sodium, I can basically erase it in my mind and replace it with a negative charge. So sodium cyanide here is going to react as if I've got a negative charge on my carbon. Sodium hydroxide is going to react as if I've got a negative charge on the oxygen. Any type of sodium sulfide is going to react as if I've got a negative charge on the sulfur, and so on. These are all, once again, circumstances in which I've got a group 1 metal, either lithium, sodium, or potassium, bonded to an atom. It's just like replacing that metal with a negative charge. Here are a few examples of weak nucleophiles. Imagine I have a molecule like this. This is called a carboxylate. An example of this would be acetic acid that we talked about in our last lecture. If you draw the loose structure out for this molecule, you will see that there's a negative charge on an oxygen and that its resonance delocalized into another oxygen. So that negative charge is being shared by 2 oxygens and is therefore not very reactive and is weak. If I've got a molecule like this, an alcohol or water, I don't have any negative charges at all. All I have is lone pairs. Now the lone pair electrons can still do substitution reactions, but they are not as reactive as having a localized negative charge on an atom. Thus, these guys are going to be weak nucleophiles. Same thing goes for thiols and for amines, as well as halogens that have negative charges on them. The strong guys, once again, are going to be the very, very reactive guys that will come in and kick off a leaving group, ba-bam, in one step, SN2, whereas the weak guys are going to be the guys who will wait around for the leaving group to take off and form a carbocation intermediate, and then they'll come in and react, okay, I guess I'll attack that carbocation intermediate like that. Strong is SN2, weak is SN1. So let's see if we can look at some examples. Determine of each of the following. We'll go SN1 or SN2 and then predict the product. Here's our first example. How in the world do we answer it? Well, we go through the questions that I delineated earlier. My leaving group's obviously going to be my bromine. It's attached to a carbon. Now I ask myself, is that carbon primary, secondary, or tertiary? This is a carbon that is stuck to 2 carbons. Therefore, it is secondary. Now remember, if it were primary, it would automatically be SN2. If it were tertiary, it would automatically be SN1. This, once again, is secondary. So that means it could be either of the above. So we have to go to the next question. Is my nucleophile strong or weak? I've got lithium stuck to iodine. Now because lithium is in group 1 of the periodic table, I can basically erase it and replace it with a negative charge and imagine that this would behave as if it were just an I-, an iodide minus. So is an iodide minus a strong nucleophile or a weak nucleophile? Well, minus charges on things are usually strong unless they're on a halogen or they're delocalized by resonance. Because this is a minus charge on a halogen, it is going to be a weak nucleophile. And weak nucleophiles favor SN1s. Thus, what's going to happen is this molecule is going to stir around long enough for this Br to take off, give me a secondary carbocation, and then the I- is going to come and take the bromine's place, SN1 style. Here's another example. I've got Br attached to a benzyl carbon. Is this a primary, secondary, or tertiary? You might be tempted to say primary, and if you did, you'd be kind of technically wrong, because this is not a traditional primary carbon. This is a carbon that is resonance stabilized. In other words, this Br could leave, give me a carbocation in this position, and have it be stabilized by resonance across 4 total carbon atoms in this molecule. Because it's not tertiary, it's not going to be SN1. So that means it's going to be somewhere in the middle. Which one is it going to be? Well, I have to ask the second question. Is my nucleophile strong or weak? I've got sodium stuck to a carbon. Sodium is a group 1 metal. I can replace it with a negative charge. This is essentially a negative charge on a carbon. And if you try to draw resonance structures, you'll see that there really aren't any good resonance structures with this carbon triple bonded to the nitrogen. Thus, this is a localized, strong, and powerful nucleophile. What types of reactions do those guys like? SN2. So what's going to happen in this case is the cyanide is going to come in with a negative charge on the carbon, attack this benzyl carbon, and kick off the bromide in a single step. Wha-bam! Giving me a CN in the place of the Br. Having fun? Good. Let's take a look at some more examples. Here I've got a Br stuck to a secondary carbon. Is it SN1 or SN2? It ain't tertiary, so it's not SN1. It ain't primary, so it's not SN2. It could be either of the above. So we go to our next question. My nucleophile, is it strong or weak? I've got a sodium I can replace with a negative charge. Is that negative charge a powerful negative charge or not? Well, you'll note that that negative charge is on an oxygen that's adjacent to a carbon double bonded to another oxygen. That is a resonance stabilized negative charge. Hence, this nucleophile is actually going to be weak. So this will be an SN1 reaction. What that means is this molecule here will stir around in solution until the bromide takes off, giving me a secondary carbocation intermediate. The negative charge on this acetate will then come in, form a bond with that carbon, and I'll have an acetate group attached to that carbon. I will, of course, get a mixture of both enantiomers in my product because it goes through an SN1 mechanism. Here's another example. I can ask my first question, is my chlorine stuck to a primary, secondary, or tertiary carbon? The answer is primary, which will, of course, go SN2. My investigation is essentially done. Nevertheless, we could still ask our question 2 just for the sake of thoroughness. Is my nucleophile / base strong or weak? Of course, I've got a localized negative charge on a sulfur. That is strong. So what's going to happen is this sulfide is going to come in, form a bond with this carbon, and in one step kick off the chloride. Wha-bam! Giving me my product in which an SH has taken the place of a Cl. Here's one more example. I've got an iodine stuck to a secondary carbon. Stuck to a secondary means it could be either SN1 or SN2. That brings me to my next question. Is my nucleophile strong or weak? I've got a sodium I can replace with a negative charge on a carbon. That negative charge does not resonance delocalize really well, so this is a strong nucleophile. That tells me it's going to go SN2. What that means is that this cyanide is going to come in with the negatively charged carbon, forming a bond with this carbon right here, and kick off the iodide in one step. Wha-bam! The final product, of course, will look exactly like this, with a CN having replaced the iodine in the starting material. One thing you should note, however, is that because this is an SN2, the product is going to have the stereochemistry inverted. That is, the bond going to the CN is going to be completely dashed and not wedged. And in theory, we will not get any of the opposite enantiomer. Alright, let's take a look at some more. In this example, I've got a bromine attached to a secondary carbon. As you've seen with all my previous examples, secondary carbon could either be SN1 or SN2 depending on the nature of the nucleophile. We look at the nucleophile. I've got a negative charge and an oxygen, and it's a negative charge that's resonance delocalized or shared across two oxygens. Thus, this is a weak nucleophile, which tells me that this will go SN1. What that means is that this product will stir around until the bromide leaves, giving me a secondary carbocation, and then this nucleophile, this acetate, will come in, forming a bond between this carbon and one of these oxygens. The product, of course, is going to have a mixture of both enantiomers because this acetate nucleophile can come in and attack from both the front and the back once that bromide leaving group takes off. Here's another example. I've got an OTS group called a tosylate group. You might be wondering, what in the world is a tosylate group? You don't have to worry about the details of that other than to know that a tosylate is a really good leaving group. Stuck to a secondary carbon, so it could be SN1 or SN2, which takes me to my next question. My nucleophile, is it strong or weak? Well, I've got water. Are there any negative charges in water? And I'm not talking partial negative charges. I'm talking localized negative charges. No, there aren't. The only thing water has is lone pairs on the oxygen. Thus, this will go SN1. Tosylate takes off, gives me a secondary carbocation. It's possible you could have a hydride shift to give you the tertiary carbocation at this position, and then the water with its lone pair of electrons will come in and form a bond at that location, give me an oxygen stuck to two hydrogens. A second molecule of water deprotonates to give me an OH coming off of this position. Here's some additional examples that I won't do for you, but I will invite you to look at and consider on your own. This brings us to a final subject: inter versus intramolecular SN2 reactions. What's the difference? Well, I want you to imagine that I've got a molecule like this which has a localized negative charge on an oxygen and a leaving group in the exact same molecule. That might be interesting. Well, you could imagine this O- coming and attacking the carbon on another molecule of itself that's bonded to a bromine like this, kicking off the bromide in an SN2 fashion. If that were to occur, I would end up getting this type of product. This type of reaction would be an intermolecular reaction, that is, in which two molecules that are separate react with each other. Now, in contrast, you could imagine this type of scenario, in which instead of attacking a separate molecule, this O- actually turned in on and attacked the carbon within itself, kicking off this bromide. If that were to occur, I would get a ringed product, as indicated here. This type of reaction is called an intramolecular reaction because the reaction is occurring within a single molecule itself, intra. So that prompts us to ask, which of these two processes is going to occur, an intermolecular or an intramolecular? Here's the answer. An intramolecular reaction is favored when doing so will form a 5 or 6 membered ring. Here's an example. I've got a negatively charged oxygen here closing in on a CH2 and kicking off a chloride. You'll note that when it does that, it gives this ring that has 6 atoms, 5 carbons and 1 oxygen. 6-membered rings are highly thermodynamically stable because each of the carbons is able to obtain very close to the ideal 109.5 bond angle required for tetrahedral carbons. The same thing goes for 5-membered rings. Thus, you could see in this example, if I have a nitrogen on one end of the molecule and a bromine on the other, the nitrogen can push its lone pair electrons into that CH2, kicking off the bromide to give me this product, which has a 5-membered ring. Note that this nitrogen, which is positively charged, still has a full octet. The reason that it's positively charged is because it has 4 bonds, which is more bonds than nitrogen wants to share in a neutral form. Now, if you want to carry out an internal, which is another way of saying an intramolecular SN2 reaction, there are 2 different ways of doing it. These are reaction conditions that I require you, my students, to memorize. In one way, I can use sodium metal. That is, if I've got a molecule that has an alcohol somewhere and a leaving group, such as a halogen, like chlorine, somewhere else, if I throw sodium metal in there, it will actually form an O- by a mechanism that I won't show you right now. And then that minus charge will come in, close on this carbon, and kick off the chloride to form a 5 or 6-membered ring. Now remember, this will only be favored if the ring size formed will be 5 or 6-membered. If it's larger or smaller, then I will get an intermolecular reaction occurring in which this molecule attacks a second molecule of itself, displacing the chloride. Second way of running this is if I treat the same molecule with a big, powerful base. This is a common base used, potassium tert-butoxide. This negative charge deprotonates this hydrogen, giving me a negative charge on my oxygen. And then this oxygen will close in on this carbon, kicking off the chloride in the exact same fashion shown up here to give me my 5-membered ring that contains an oxygen in the middle of it. One thing I want to point out is this. If I had a base here that could actually act as a nucleophile, such as hydroxide, instead of deprotonating this OH, what would happen is it would actually just come in here and kick off the chloride and take the chloride's place instead. Now you might be wondering at this point, what is the difference between a nucleophile and a base, and how do I distinguish between the two? Well, please hang on to that question. I promise it will be resolved in a later lecture. For now, what I plan to do with people who are taking my class from me live is spend the duration of my class period working together on various problems from Chapter 8. For people who may be just watching this on YouTube, rest assured that I will post footage of that lecture material on YouTube to help supplement your learning of this wonderful and magical, indeed wagical topic of substitution reactions. Until next time, have an enjoyable rest of your day.